All right, so get this. You sent us a paper on anti-skyrmions,
Oh, wow.
which means you're already diving into some seriously cool, cutting-edge physics.
Yeah, and trust me, this isn't just another theoretical particle.
Yeah.
This is the kind of stuff that could revolutionize how we use and store data.
We're talking faster computers, entirely new forms of memory. But hold on, let's back up a bit.
Okay.
For those not familiar with the world of magnetic particles, imagine tiny little tornadoes of magnetism inside certain materials.
Mm-hmm.
These are called skyrmions.
Right, they're like little magnetic whirlpools with a special property topological protection.
Okay.
Think of it like this. You have a knot in a rope. You can push and pull it all you want, but you can't undo it without untying it completely. That's what makes skyrmions so stable.
Interesting.
And interesting for data storage.
They're like these robust little containers for information, but what's really cool is that this paper isn't just about skyrmions, it's about their even more elusive counterparts, anti-skyrmions.
Yeah, and that's where the real mystery begins. We've seen skyrmions in a bunch of materials, but anti-skyrmions, they've been like the yetis of the magnetic world. Rarely, if ever, observed in the same way.
So how do you study something that almost never appears? They didn't just pull out a Ouija board, did they?
Thankfully, no. They turned to the power of Monte Carlo simulations, which is basically like running a massive game of magnetic chess on a supercomputer.
So they created this virtual sandbox where they could test out different scenarios and see if they could coax these anti-skyrmions into existence.
Yeah.
What did they find?
One of the big breakthroughs was understanding the importance of something called the Dzyaloshinskii-Moriya interaction.
Okay, we might need a simpler name for that. But
Yeah.
seriously, what does this DM interaction do?
Think of it like a dance choreographer for those magnetic spins.
Okay.
Depending on the type of DM interaction, the spins will arrange themselves in completely different ways, forming different types of magnetic dances, like a waltz for Bloch skyrmions, a tango for Neel skyrmions.
And for our elusive anti-skyrmions, what kind of dance move are we talking about?
That's the exciting part. They found a specific type of DM interaction that leads to these anti-skyrmions forming a stable, repeating pattern. We're talking about a whole anti-skyrmion lattice phase, like finding not just one snowflake, but a whole blizzard of them, all perfectly arranged.
Now that is cool. And if you're following along with the paper, figure 2 shows this lattice structure visually. It's pretty amazing.
Yeah, and this isn't just some theoretical curiosity, it's a potential game changer. You see, if we can control these anti-skyrmions, they could be even better than regular skyrmions for data storage and processing.
Hold on, even better. How is that possible? This is where we need you to break it down for us.
Because of their unique properties, anti-skyrmions could potentially lead to faster, denser, and more energy-efficient devices.
Okay, now we're talking. But let's go back to this anti-skyrmion lattice for a minute.
Sure.
How did they even discover it in the simulation? Was it just hiding in plain sight?
That's where it gets even more interesting. They created a phase diagram that's figure 3 in the paper, which is like a treasure map, showing the exact conditions where these anti-skyrmions are most stable.
So it's like they found the recipe for cooking up a batch of anti-skyrmions.
Exactly. The right temperature, the right magnetic field, and boom, you get this incredible lattice structure. It's like they've given us the blueprint for creating these things in the real world, which is a huge step.
So they've given us the map, but can we actually follow it? Finding these anti-skyrmions in a simulation is one thing, but what about in the real world?
That's the million-dollar question, isn't it?
Yeah.
And the paper doesn't disappoint. It actually points to a specific type of crystal structure, those with something called D2D symmetry, as being particularly promising for hosting anti-skyrmions.
D2D symmetry sounds like we're getting into some serious crystallography here. But for those of us who aren't material scientists, what's so special about this particular structure?
It all comes down to the arrangement of atoms within the material. Think of it like building a house of cards. The way you arrange those cards determines whether the whole structure stands or collapses. D2D symmetry creates the perfect house of cards environment for those anti-skyrmions to form.
So it's like this specific crystal structure provides the ideal scaffolding for those magnetic whirlpools to do their thing.
Exactly. It all comes down to that DM interaction we talked about earlier. The paper suggests that in materials with DTT symmetry, the DM interaction has just the right strength to allow those anti-skyrmions to form that stable lattice structure.
Okay, so we've got our treasure map with the crystal structure, but I have to ask the million-dollar question. Have we actually found any materials that fit the bill?
That's where it gets even more intriguing. While we haven't yet found a naturally occurring material that checks all the boxes, the right elements, the DTT symmetry, and the perfect DM interaction strength, The fact that we can now simulate these anti-skyrmions with such precision means we can be a lot smarter about our search.
So no anti-skyrmion smartphones hitting the shelves tomorrow.
Not quite yet. But this research is like shining a spotlight on exactly where to look. Instead of blindly searching through every material on Earth, we can now focus our efforts on those with D2B symmetry. It's like knowing the treasure is buried somewhere on a specific island rather than somewhere in the entire ocean.
And this is where it gets really exciting for me because we're not just talking about finding a new particle here. We're talking about potentially creating entirely new materials, materials that have never existed before.
Yeah, you're absolutely right.
Wow.
And that's the beauty of this kind of fundamental research. It's not just about understanding what's out there. It's about pushing the boundaries of what's possible. We might discover that the perfect material for hosting anti-skyrmions at room temperature doesn't even exist naturally.
So we'd have to create it ourselves. That's incredible.
It is incredible, and it's something that scientists and engineers are already working towards. There's a whole field called material science, dedicated to designing and synthesizing new materials with tailor-made properties.
So we're talking about potentially cooking up these materials in a lab, atom by atom, until we get that perfect recipe for anti-skyrmions.
You got it. It's a bit like having a blueprint for a futuristic device, but the materials to build it don't exist yet.
Okay, so let's say we manage to pull this off. We find or create the perfect material, it's stable at room temperature, and we can control these anti-skyrmions at will. What changes for you and me, for the average person? What does this actually look like in the real world?
That's the question, isn't it? And this is where it goes from being a fascinating scientific discovery to a potential technological revolution. Let's start with computers. Imagine a world where computers aren't just a bit faster, but orders of magnitude faster than what we have today.
No more staring at loading screens. Sign me up.
Exactly. Because anti-skyrmions are so much smaller than the transistors we currently use in electronics, we could pack significantly more computing power into a much smaller space. Imagine smartphones that are as powerful as today's supercomputers.
Okay, now you're just making me impatient for the future.
And we're just getting started. Remember those stable, controllable magnetic whirlpools? Think about data storage. Instead of using magnetic domains like we do in hard drives today, imagine using anti-skyrmions to represent bits of information. We could potentially store vastly more data in a much smaller space.
So say goodbye to clunky hard drives and hello to tiny devices that can store entire libraries.
You're getting the idea. And because these anti-skyrmions are so stable thanks to that topological protection, we're talking about data storage that could potentially last for centuries, maybe even longer.
Wow, no more worrying about losing all your photos and files.
And it's not just about quantity, it's about efficiency too. Because we can move these anti-skyrmions around with very little energy, we could create incredibly energy-efficient devices. Imagine data centers that use a fraction of the power they currently do, significantly reducing our environmental impact.
Okay, so faster computers, more storage, less energy consumption. This is starting to sound almost too good to be true. But we've got to be realistic here. Every new technology has its challenges. What are the potential roadblocks we might encounter with anti-skyrmions?
That's a great point. It's important to remember that we're still in the early stages here. One of the biggest challenges will be figuring out how to reliably control and manipulate these anti-skyrmions at scale.
So going from those beautifully arranged lattices in a simulation to a jumbled mess in the real world.
Exactly. We need to figure out how to write information into those anti-skyrmions, how to read it back out, and how to do it all quickly and reliably, billions of times over. It's a bit like trying to herd cats. But instead of cats, we're talking about tiny, invisible magnetic whirlpools.
And I'm guessing we haven't quite perfected our anti-skyrmion herding skills just yet.
Not quite. There's a lot of research and development ahead, but that's what makes this so exciting. We're talking about pushing the boundaries of what's possible, exploring a whole new realm of materials and technologies.
Yeah, it sounds like we're standing on the edge of something truly groundbreaking. But like you said, it's still early days. We've got the map, we've got the vision.
Right.
Now we need to figure out how to make it a reality.
And that's where the real work begins. But that's also what makes this such an exciting field to be a part of, because we're not just talking about incremental improvements here. We're talking about potentially revolutionizing the entire way we think about computing and data storage.
It's like we're at the dawn of the next Silicon Valley, but instead of silicon chips, we're talking about anti-skyrmions.
And who knows what amazing devices and technologies this new era will bring. Maybe we'll see anti-skyrmion-powered sensors that can detect diseases at their earliest stages. Or maybe we'll finally crack the code on quantum computing, all thanks to these tiny magnetic particles.
The possibilities really do seem endless, but for our listener who sent in this paper and sparked this whole incredible conversation about what's the key takeaway here, what should they be most excited about?
I think the biggest takeaway is that we're on the verge of a major paradigm shift in how we interact with information. And this isn't just science fiction. This is real, tangible science backed up by years of research and incredible discoveries like the one we've been discussing today.
So it's not a matter of if, but when we see these anti-skyrmion technologies become a part of our lives.
Exactly. And that's a future I'm incredibly excited to be a part of. And who knows, maybe, just maybe, our listener will be the one to make that crucial breakthrough, to find that elusive material or develop that groundbreaking application that changes everything.
Now, that would be something, wouldn't it, to be the one who unlocks the full potential of anti-skyrmions, but even if our listener doesn't end up building the next generation of supercomputers, we hope this deep dive has left them with a sense of wonder and excitement about the hidden world of magnetism.
Because sometimes the smallest things can lead to the biggest discoveries, and who knows what other secrets are waiting to be unlocked.
Hmm.
All it takes is a curious mind and a willingness to dive deep into the unknown.
So, to our listener, keep exploring, keep asking questions, and keep those sources coming because we can't wait to see what amazing discoveries we uncover together next time on the Deep Dive.